Okay, question number 7. Now, in question number 7, we have a spring-loaded system. So we have the opposite of a collision. We have separation, kind of like question number 1. The difference is we're not just going to be satisfied with analyzing conservation momentum to find final velocities. We're also going to find the kinetic energies of both cars and use that to figure out the spring constant that is actually compressing the spring too. So this is a combination of conservation momentum mixed with conservation of energy. Put your name in. Let's begin. So the first thing we want to do is note the information. So the spring is compressed 144 millimeters. Let's note that. Which, by the way, would be 0.0144 meters. Make sure you convert it. Okay, you have the mass of both cars, I think. Yes. So make sure you record both. Okay, so mass 2 is going to be 152 plus 500. That should be 652. Right, which is the same as 0.652 kilograms. Okay, cart 1, 279 plus 500 should be 779. Let me double check that. Or 0.779 kilograms. So we get that information, okay? Both are starting at rest, okay? So both start with zero momentum. They're going to fly off in opposite directions, just like question number 1. So what we're given, once we note the compression, we're going to activate the plunger by pushing that down, and they're going to fly apart. Now we know the velocity of this cart after collision. We know V1 prime. It's 2.623 meters per second in my case. Write yours down. And we first have to find V2 prime. So that's the first thing we have to find, okay, is the momentum of car 1 to get the momentum of car 2. So if you look at what we have to find, okay, we have to find the total kinetic energy in the spring constant. So this is going to be essentially our path. We're going to find total momentum we know the total momentum is 0, so we're going to find the velocity of car 2 after collision, okay, using conservation of momentum with separation. Then what we're going to do is we're going to calculate the total kinetic energy of both cars. Now, that's easy. It doesn't matter the direction. Energy has no direction, so just simply add them up. Then we're going to use conservation of energy to suggest that the elastic potential energy, the spring potential energy that you start with, that's the initial energy, equals the final kinetic energy as they fly apart. Well, you're going to know this because that's your total kinetic energy. So you can use the final kinetic energy, set that equal to the initial kinetic energy, or initial potential energy, and we know that the spring potential energy is 1/2 kx squared. So that, guys, is how we can solve for k, the spring constant. So that's going to be our plan in terms of how we're going to attack this, okay? So first things first. We did fill out all the information before and after they separated. I just wrote it kind of differently, so I'm just going to move that down here. Let me go. Put you back there. Okay, now we're good. All right, and we don't know, oopsie. We don't know V2 prime. Okay, so first we're going to use conservation momentum to find the velocity of car 2. The way we do that is if initial momentum equals final momentum, then 0, which is the initial momentum, they're not moving, would equal m1 v1 prime plus m2 v2 prime. And we're just going to solve that equation for v2 prime. Okay, now in order to do that, you can see we're going to have to subtract this, right? And then divide by this. Okay, so, oops. So v2 prime is going to be equal to negative m1 v1 prime divided by m2. So go ahead and plug in your information. So my mass 1 was 0.779 kilograms. Its velocity after was 2.623 meters per second, all divided by mass 2, which was 0.652. See, that cancels. Okay, now our answer should be negative. We can see it's negative because velocity 2 is going to the left, but make sure we account for that. Go ahead and take a moment to plug in your values. I'll plug in mine. Okay, and I'm getting a value of negative 0.313 meters per second. Okay, so that's my velocity of car 2 going to the left. Well, now in step 4, we're going to find the kinetic energy of each one. So let's find the kinetic energy of each one, and then we'll add them. So kinetic energy 1, we'll call that K1. And kinetic energy 2, we'll call that K2. So 1/2 m1 v1 squared and 1/2 m2 v2 squared. Just plug in, and then we'll add them up. So 1/2 times m1, if you recall, was 0.779. Velocity afterwards was 2.623, and then we have to square it. And then the second one was 0.652, and its velocity. Now, its velocity was negative, but realize you're squaring the velocity. So for the purposes of this calculation, you don't have to put in the negative. Just put in the speed, 3.13 meters per second. Okay, please take a moment to find the kinetic energies of each one afterwards. Okay, I'm getting 2.68 joules for the first one. And about 3.19 joules for the second one. So my total kinetic energy is just going to be the sum of those two. Just add them up. And we get 5.87 joules. Okay, so far, here's what I have. Okay, I need the momentum of car 1. Okay, so that one's just going to be 0.779 times 2.623, because that's the first thing we have to enter. .04 kilograms meters per second. Our total kinetic energy. Okay, now we need to find our spring constant. And here's how we're going to tackle that. We're going to set our our final kinetic energy. So if we're using conservation of energy, which tells us total initial energy equals total final energy. Well, initially we start off with spring potential energy. Call that U sub S. And that's equal to K my final kinetic energy. So 1/2 kx squared will equal 1/2 mv squared. But I don't need to write it as 1/2 mv squared, because if you realize, I've got the value for kinetic energy right here. So we'll just replace a number. So I'm going to keep it as K final. Okay, now I need to solve this equation for K. Lowercase k is the spring constant. So to do that, I'm going to multiply by 2 and divide by x squared. That'll get rid of everything I need to. Then we can plug in. So K is going to be 2 times the final kinetic energy over the compression distance squared. So 2 times 5.87 divided by point, I think I wrote it down. The compression was 0.144 meters. 0.144 meters, and then don't forget to square that. Okay, let's put that in our calculator. And I'm getting about 566 newtons per meter. 0.16, but I'm just going to round it to the nearest whole number. All right, let's take a peek and let's see how we did. And there we go. So this was our first crack at looking at conservation of momentum and conservation of energy consecutively. So one concept following the next. In this particular case, momentum came first, energy came second. That's not always the case, okay? But in this case, it was. So just remember the final variable of one concept, in this case, conservation of momentum, became the initial variable for the other concept, in this case, conservation of energy. And the velocity of cart 2 was the thing that linked them both. Okay, so if you have not gotten question number 7 right, pause the video and try it yourself. On to question number 8. Now, in question number 8, we're dealing with another multiple concept scenario. You've got a mass that's going to fire and embed itself, so it's going to get stuck in a second mass that's at rest. The two masses will combine together, and they will then pass through a loop-de-loop, okay, a circular loop, vertical loop. The entire situation is frictionless. But here's what we have going on here. In this particular part of the problem, you have a collision right here. Specifically, you're going to have an inelastic collision because the two masses will stick together. So we have conservation of momentum happening right there. Then the two masses are going to combine, and they're going to fly to their highest point. In which case, well, any point really on that circle, doesn't matter. In which case, you have a change in energy in this closed frictionless system. You're starting with kinetic energy, and you're ending with gravitational potential energy. In which case, we can use conservation of energy to relate these two energies. Now, the other thing that also exists at this problem is the fact that it is a circle, okay? And with circles come the possibility of centripetal forces. Right? Net force equals mv squared over r. Okay, in other words, causing force pointing in minus opposing force pointing out equals mv squared over r. So that's what's going on in this problem. So we see in step 1, draw the forces at the top of the block such that it's going over the loop with the minimum speed. There we go. So we're going to draw the block up here. Now, normally, you would have normal force and you would have weight equals mg. However, because we're talking about the minimum speed needed to get over the top, you will neglect the normal force, okay? So the only thing we have going over the top, forces pointing in minus forces pointing out equals mv squared over r. There are no forces pointing out, and the only force pointing in is mg. So we're going to solve that for the minimum speed. You can see the masses are going to cancel, multiply by r square root, and the minimum speed, V min, is going to be the square root of g times r. Let's go ahead and find that. Okay, now, what you're going, don't assume g is going to be 9.8, okay? Don't assume that. In fact, let's see, we're given the mass and velocity of the first block. No, we need to find the velocity of the first block. Given the mass of the first block, mass of the second block, you are given the radius of the circle, and it looks like you do get to use g equals 9.8. Yeah, it doesn't tell us otherwise, but just don't assume that, okay? So we're going to go 9.8 times the radius, which is, the radius, keep in mind, is 21.8 in my case. Right, you know, obviously write down yours, but that would be 0.218 meters. Make sure you convert it before you do this calculation, okay? So 9.8 times your radius, okay, and then the square root. Okay, I'm looking at 1.46 meters per second. Okay, that is my, okay, so speed 1, just so you know, speed 1 is before the collision, speed 2 is right after the collision, speed 3 is at the top of the loop. So we just found speed 3, 1.46 meters per second, okay? Actually, we just did step 2. You can just draw an arrow to this right here, but basically all that was supposed to go down there. Step 1 was just drawing the forces. Okay, now for step 3, let's work the problem backwards. Now that we have the speed up here, we can use conservation of energy to find the speed down here right after the collision. So using conservation of energy, we know that energy initial at the bottom equals energy final at the top. So that's going to be initial kinetic energy equals final kinetic energy plus mgh. And we're going to change this into 1/2 mv squared, I guess initial, equals 1/2 mv final squared plus mgh. And you're solving this for v initial. So you have to multiply by 2. Oops. You have to multiply everything by 2. Okay, divide out all the masses. Cancels everywhere. And then finally square root. So the equation we're working with is v final is equal to v initial squared plus 2gh. Okay, that's what we're left over here, and we're going to plug into that. Okay, so my v initial, sorry, got this backwards. Didn't mean to confuse you. That's v initial, that's v final. Had it backwards. So v initial equals v final squared. There we go. That's better. Sorry if I was confusing you there. So we have 1.46, or whatever the speed you got over the top, plus 2 times g times h. Now, h is going to be twice your radius, because there's your radius, but the entire height, you can see, is going to be radius plus radius. So we're going to go twice your radius. So the radius is, in my case, 0.218. Double that, and we're looking at 0.436. Okay, so I'm going to go 1.46 squared plus 2 times 9.8 times 0.436. Then we need to square root that. Please go ahead and find your velocity after collision. Mine is looking at about 3.27 meters per second. Okay, now the final step is to continue to work backwards, much like we did with the ballistic pendulum lab, and find the velocity before collision. So now we're looking at conservation of momentum. So we have m1 v1 plus m2 v2, which is going to be 0 because m2 is at rest before collision, equals the combined mass of m1 plus m2 times v prime. Now, the speed you just found right here, that is v prime. That is the speed after collision. Okay, so you're solving this for v initial. So basically, we just have to divide by m1 and we're good. So v1 is going to be m1 plus m2 times v prime divided by m1. Please don't cancel those, right? The plus here forbids that. So adding your two masses, now for me, I'm going 6.3 plus 19.4, and then I got to convert from grams to kilograms, so let's move that decimal 3 to the left. And I'm looking at a combined mass of 0.0257 kilograms times 3.27 divided by mass 1, which is going to be 0.0063 kilograms. Times 3.27 divided by 0.0063. All right, and I'm getting about 13.3. Go ahead and put your calculations in and see how you did. All right, and there we go. Hopefully you're able to get question number 8 correct as well. All right, on to question 9. Angle of a ballistic pendulum. Now in this one, we're going to be firing a ball into a box. The ball's going to get stuck into the box, and these two are going to swing upwards to some highest point, just like this, wherever that highest point is. Now, in this problem, we'll first go ahead and enter your name into the program. In this particular problem, you're looking for the speed after collision right here. And keep in mind, if the ball is getting stuck into the box, we have conservation of momentum to start with, but specifically that's going to be an inelastic collision. Okay, and the velocity after collision is the same as the initial velocity of the box and the ball as they begin their upswing. And ultimately, we also want to find this maximum angle to which it rises to. Okay, so we'll get to that part in a minute. First, take a moment to label everything in your problem. Okay, now first thing I would be aware of is you look at there, you're given the gravitational field. In my case is 8.4. Don't assume it's going to be 9.8. It's not always. Okay, I'm given the mass of the ball, which I'm going to call mass 1. That's 183 grams, which is 0.183 kilograms. I'm given V1, the velocity of the ball, is 49.5 meters per second. I'm given M2, which is the mass of the box, 7.099 kilograms. And V2 would be 0 because the box is starting from rest. Okay. So I'm going to use conservation momentum, okay, with an inelastic collision to solve for the velocity after collision. It's the first thing I'm going to do. Okay, now the equation I will use is m1 times v1 plus m2 times v2, which we know is going to be 0 because, well, it has no momentum before it collides. Box is just hanging there. And that's equal to the sum of your masses, m1 plus m2, times v prime. Now v prime, when you see that prime notation, that's the velocity after collision. Okay, so that's ultimately, guys, what we're looking for here. We know we can get that by just simply dividing by the sum of the masses. So let's do that. Okay, cancels here, cancels here. And that's going to be our v prime. So it's going to be m1 v1 over the sum of your masses, m1 plus m2. Okay, m1 is 0.183 times V1, 49.5, all over 0.183 plus 7.099. So go ahead and fill out your values. I'll fill out mine. Okay, and we're going to go find the, let's see, 0.183 times 49, whoopsie, 0.5. Okay, I'm looking at 9.0585 kilograms meters per second over 0.183 plus 7.099. Okay, I'm looking at 7.282 kilograms. Okay, what do we got? Okay, V prime. Let me go ahead and divide those two. So 9.0585 divided by 7.282. Okay, I'm looking at a very slow velocity of about 1.24 meters per second. Okay, that's going to be my velocity here, the speed after collision. Okay, so 1.24. Now, we're going to get the angle part in a sec, but before we do that, the way we're going to do that is we're going to use conservation of energy to describe the upswing, because you're going to start with kinetic energy initially at the bottom, so 1/2 mv squared. At the bottom, you have no potential energy, so it's the lowest point of the problem. Okay, now at the top, you do have potential energy, which is equal to mgh. You do not have any more kinetic energy because the mass comes to rest. Okay, so what we really know is the initial kinetic energy you start with transforms into gravitational potential energy at the highest point. And in order to find theta, you need to solve for h. Let me explain. This is your h. It's the distance from where the center of the box is to where the center of the box was. That's h. Now, this whole part here is L, the length of the string, which, by the way, is the length over here, too. Okay, but this side over here, that is L times the cosine of theta. Okay, so we know that L is equal to h plus L cosine theta. So in other words, to solve for h, I have to subtract L cosine theta. So h is equal to L minus L cosine theta. So I'm going to need that. So I've got to solve for h, and then I'll use that to solve for cosine theta. Okay, that's going to be our plan. So here we go. Conservation of energy. Okay, we know that energy initial equals energy final, which is going to be initial kinetic energy transforming into final potential energy, which is 1/2 mv squared, and that's equal to mgh. And we just have to solve that for h. So to solve for h, we need to divide by mg. You'll notice the mass cancels on both sides. And you can either look at this as 1/2 v squared divided by g, or you can look at it as v squared divided by 2g. Because remember, multiplying by half is the same as dividing by 2. I think that's how I'm going to choose to recognize it. H is equal to v squared over 2g. Okay, so you're going to take your speed after collision, 1.24 meters per second, square it. Okay, divided by 2 times. Now my gravitational field constant is 8.4. Don't use 9.8 unless it says. All right, so I'm going to go open parentheses, 1.24, close parentheses squared, divided by open parentheses, 2 times 8.4, close parentheses. I'm looking at a really small height of about 0.0915 meters. Okay. Now, back to my original thing here. H is equal to L minus L cosine theta. And what I'll do is I'm going to add L cosine theta to the left, and I'm going to subtract height H over to the right. And if I rewrite this, I get L cosine theta equals L minus H. And so I will then divide by L, and I'll have cosine theta by itself. That's what I'm going to be plugging into. So cosine theta is going to be equal to L, which was, in my case, now it's 164 centimeters in my case. You can see that right here, which would be 1.64 meters. So just make sure you convert it. So I'm going to go cosine of theta equals 1.64 minus my really small height that I got, 0.0915. And then I'm going to divide that by the L again, which is 1.64. It's really important that you understand that the sine or cosine of an angle can never be greater than 1. If that happens, you're going to get an error undefined message in your calculator, okay? So let's figure this out. 1.64 minus 0.0915. Is that divided by, again, 1.64. Okay, so my equation says cosine of theta equals 0.944. Now remember, to solve for theta, you just have to take the arc cosine of both sides. That's how you solve it. Cancels, cancels. Theta equals the arc cosine of that value. Okay, and I'm getting about 19.2 degrees. I'm just going to double check my work one more time. Okay, the arc cosine of 0.944. Yeah, about 19.2, 19.3. Okay, so I'm going to enter that in. 0.2. All right, now I'm going to check, see how we did. It'll fire, it'll rise, and hopefully it'll rise to the angle you said it will. And mine did. Mine rose a little over 19 degrees. Okay, so that's how we do question number 9. It's a conservation momentum problem, inelastic collision specifically, and then it's a pendulum upswing, which would be a conservation of energy problem. Sequentially, that means back to back. All right. At this point, go ahead and pause the video and make sure you can get this question number 9 correct yourself. Okay, on to question 10, our last and final question. Right angle curling stone problem. Well, what we're going to deal with in this one is we're going to deal with momentum in multiple dimensions, in 2 dimensions specifically. Okay, and so all we have to do is account for an inelastic collision, just like we did before. Okay, this equation here, but we're going to apply that in the x direction for horizontal and the y direction for vertical. We're going to apply it simultaneously, but independently. Okay, I'll show you what I mean. First thing I think you should do is take a second to list your information. All right, I'll do the same. Okay, so I'm going to call this bottom mass, I'm going to call that M1. Okay, and for me, it's 10.4 kilograms. And V1, I'm given, is 3.59 meters per second. Now notice it's going straight up, okay? Now, your angles are given right here. 0 degrees is to the right, up is 90, left is 180, down is 270, and back to right again is 360. So 360 and 0 are the same. Okay, now another way to think about it is this is only going in the positive y direction. So it only has positive y momentum. Okay, I'm going to call this one M2, 22.9 kilograms in my case, and V2 would be 2.17 meters per second. Now, since it's going, in my case, it's going to the left, so you're going to have to account for your directions. If you have an arrow going down or left, that's negative velocity, and you do have to account for that. Okay? So just be aware of that when you're putting in your values and computing, okay? Okay, so that's before collision. Okay, now what we're going to do is we're going to solve for the speed afterwards. Okay, and then what's going to happen is they're going to bounce off each other, and then we're going to get an idea of exactly where they ended up, and we'll see it in this bottom graph down here. Okay, ready to do this? Here we go. We're going to apply, remember, it's an inelastic collision, so it's conservation of momentum. Okay, but it's an inelastic collision. And now remember, the concept of inelastic does not mean stick together. You can use that to visualize the problem. That's not what defines it. An inelastic collision is defined as a collision where kinetic energy is not conserved. Momentum is always conserved in a collision, but when kinetic energy is lost, that is an inelastic collision. A perfect inelastic collision, that is one in which one object sticks into another. Okay, so it's an inelastic collision, and the equation for it is m1 v1 plus m2 v2 equals m1 plus m2, the quantity of m1 plus m2, times v prime. Okay, so what I'm going to do is I am going to copy this equation down. In fact, I'm going to section off this middle part here into two halves. Okay, so we're going to do horizontal first, right, left, and then I'll do vertical. Okay, so copy the equation down. Now, what would it look like horizontally? It just simply means everything is applied in the x direction. Okay, now, mass 1 is only moving in the y direction, so it has no horizontal momentum. Okay, but m2 is moving to the left horizontally, so it does have initial momentum. So we're going to solve this for v prime x. Or vx prime, I guess is how we would say it. Okay, so Vx prime, or V horizontal prime, is going to be mass 2, which in my case is 22.9 kilograms, times the velocity. In my case, it's going to be negative 2.17 meters per second. So try to account for positive and negative velocities when you're doing these, okay? And I'm going to add my masses together, 10.4 plus 22.9. Okay, I'm going to figure out what Vx prime is. Okay, so parentheses, 22.9 times 2.17 negative, close parentheses, divide, open parentheses, 10.4 plus 22.9. Okay, I'm getting a velocity of negative 1.49 meters per second. Okay, so that's my horizontal final velocity. Okay, my vertical final velocity, because if I have these two objects that are going in this direction, doesn't it make sense that when they stick together, they're going to kind of go off somewhere in this quadrant right here? Well, we're going to figure that out, and we're going to figure out the angle to which it goes to here, which is going to be that angle above the horizontal. Okay. Now, again, I'm going to copy down that same equation, but this time we will apply it in the y direction, just like that. And you're solving for Vy prime. Now, if I look carefully at this here, I know that mass 1 does have y momentum. It does have vertical momentum, but mass 2 only going in the horizontal direction does not. So I get to cancel those right here. Again, I'm going to divide by the sum of my masses. Okay, and so Vy prime is going to be M1, which was 10.4 kilograms, times V1, 3.59. Since it's going upwards, we'll consider that positive velocity. 59 divided by the sum of the masses again, which would be 10.4 plus 22.9. Okay, so I'm going to go open parentheses, 10.4 times 3.59, close parentheses, divided by open parentheses, 10.4 plus 22.9, close parentheses. Okay, I'm looking at a velocity here of about 1.12 meters per second. Okay, so I know that it's going more in the x direction than it is the y direction. So I expect my velocity after collision to be this right here. It's going to have a velocity that is going in the x direction. If this is v prime, we're going to call this v prime x. And we're going to call this side over here v prime y. Okay, and how are we going to solve it? Pythagorean theorem. V prime is going to be v prime x squared plus vy prime squared. Okay, negative 1.49 squared plus 1.12 squared. All right, and we're going 1.49 squared plus 1.12 squared. That's 3.47. I'm going to take the square root of that. And I'm getting 1.86 meters per second. Okay, now to find the angle, the direction of it, I'm going to use the arctan equation. Arctan of the y component, or the vertical component, over the horizontal component. (1.12) over negative 1.49. Okay, so 1.12 divided by 1.49 negative. Divide those, got that, arctan. Okay, so I'm getting negative 36.9 degrees, and that makes sense because you're going, this angle here is going clockwise. From clockwise angles go negative, or I can go positive here, which is just going to be 180 minus. So, in other words, 143.1 degrees. I can enter either of those in. Okay, so it's either this or 143.1 degrees. Okay, let's enter in our values. The speed, 1.86. The heading, I'm gonna put in the positive angle, just 143. And there you go. Works out. So just note that a problem like number 10, it's an inelastic collision problem like we did before. The only difference is we have to apply inelastic collision properties in the horizontal and vertical direction. Ultimately, we'll use Pythagorean theorem to find the hypotenuse of the final velocity vector, and then we'll use the arctan formula to find the heading or the angle in which it goes. Well, I hope you were able to get these questions correct. If not, please pause the video, try it again. And if you're still stuck, write a bunch of question marks where you are stuck and come and see me so I can help you. All right. I will see you next time.